So we saw two methods of accessing the memory, and the difference between method 1 and method 2 is that uh, of course the structure is completely different, but in the case of method 1 it dereferences at the macro level. That is, uh, when you do ADDRW and y- and you put this expression, it dereferences it at the macro level. In here, method 2, as this is a CMC standard assuring better code compatibility due to its popularity and is simpler to use. And the method 2 dereferences at the structure pointer axis, that is the arrow operator. So that's the difference between these two methods. And we saw how the methods are implemented, and we decided that we are going to use method 2 because it's compatibility with the CMC standard. Now let's come to bitwise operators. Now, this is another, besides accessing memory, we also need to operate on the bits and bytes of the registers and other memory locations. So read, modify, write bitwise operators read values to a temporary location first, modify the value, and write back the value, overriding the old one. Bitwise OR is used to set bits in a register or a memory location. Bitwise AND is used to generally clear bits in a register or a memory location. Bitwise XOR is used to toggle bits in a memory location, and left or right shift operators, that is a less than and a greater than sign, to move bits to a particular bit location in a memory region or register. So we are going to see each operation one by one. So let's say we are setting bit positions in a read write memory location or a register. So this is a general purpose IO GPIO register, and we need to say set the bit in location 3 here. So GPIO D. So we want to enable the GPIO D block. So to enable the GPIO D block, we have to set the bit here. So far we have just been writing a complete 32-bit value into the register. So that is not always how it should be done. So you need to sometimes address that particular bit only. So what we do is generally to set bit positions with all ones and OR operation is sufficient. We generally use left shift predominantly while configuring registers. We cannot set the field to 0 with this method if the bit position is already 1. So we use bitwise OR for this purpose. Now, so say this is in position 3. Okay, what we generally do is we declare a variable of, say, type unsigned int, like we did, and say some variable, and then do equal to, and see we take 1, so 0x1. So we take the value 1 because we have to set 1 bit here. If we had to set 2 bits or 3 bits here, we will take the value accordingly. So you could take it as a hex 1, or you could take it as a binary 1. Either ways it is fine. Sometimes what happens is, when you have say 4 or 5 bit fields to set, always so you have to find out the, say, hex for, say, 5 ones, suppose. So 1 1 1 1 1. So there are 5 bit fields you have to. So this is in hex, it is 1f, but if you want to keep it more in a more understandable format, you can actually do 0b 1 1 1 1 1. So this will be taken as individual bits. So you can do that as well. But nevertheless, in here, let's say we have taken a 0x1. So 0x1 and 0b1 are the same thing. So x1 and binary one are the same, but this is in position 3. So what we generally do is we left shift by 3 positions, so 1 2 3. So this is how we do it. So we left, so this value is actually 1000 with 28 zeros here, because this is a 32-bit register and we have declared it as a UINT 32, right? So we have 28 bits here. So this is what the value comes to once we do this. Okay. After doing this, so this one we saw, that is, RCC is another set of registers, and AHB is a register where you enable. So RCC is basically a structure that it's like the structure that we saw yesterday, and one of the members of that structure is AHB1ENR, which also happens to be this register. And then we do RCC AHB1ENR equal to, and then we do OR equal to, that is, whatever value we obtained from here, we OR that value with this particular register. So basically the intention of doing that is rest of anything that is ORed with a 0 stays as it is. So we are not touching or we are not disturbing any other value. We are just changing this value to 1. If we had made it equal to, rather than, so if we just set it equal to that, it would have overridden the other values, which is not the intention here. The intention here is just to set this bit and leave the other values as they are. So leave the other values alone, and just if there is a necessity of changing all the bits in the register all together, that is, so there you don't need to do this. You just need to do an equal to, because everything is overridden in that register, because you're just writing a count value there. But mostly in such registers you will be having to set and read from only portions of those registers. You are not supposed to change everything all at once. So this is the method for setting a bit position. So UINT 32 variable, and then you do this 0x1 or any field width, and then move it that many locations, and then whatever value you have got here, you OR it with the value that is already there. So RCC AHB1ENR is the value that is there in that register, and we saw how to read the values, right? So this is how the value is read, and we just OR that value with what we obtained here, and thus this one is set. If this is already set, say it is already set, and we do this again, it has no effect, because 1 or 1 is 1. So, but this method cannot be used for setting this to 0. So suppose you want to, so just like you need to set a bit, you would need to clear a bit also. So clearing a bit, again we need to follow a slightly different we need to put in a different expression for clearing the bit. Scenario 2 is setting and clearing multiple bit positions in a read-write memory location in the register. So now what we are doing is we are setting and clearing multiple bit positions. So what needs to be done is, in this register, this is a register to set the mode for GPIO out. Okay, so this is actually for the LEDs that we have on the discovery board, and these are the 4 sets of fields, that is each comprising of 2 bits, that we need to set in order to configure the LED ports. Okay, that is the ports which we will be using to switch on and switch off the LEDs. So we'll see the GPIO setting later. That is how all of this is done. This is only to show you how the registers are operated on. So let's say that we have now what happens is, like I said, here you have 1 2 3 4 5 6 7 8 bits here that need to be worked on. So we don't know what the setting is previously, and we don't need to keep the settings as they are. So basically we can clear this field. So how do we clear this field? So we have a few methods to do it, in the sense, not a few methods, but the same method, but we can express it in different ways. So here you can see one variable, that is LED PIN pins clear. So LED pins clear. Okay. Now, like before, instead of a 1 you have to put FF, right? Because it's 8 bits. 8 bits in hex is FF. Or you could also do this 0B 1 1 1 1 1 1 1 1. Either ways it's fine. But not only that, in which position is it? It starts from bit number 24. So you have to left shift it to bit number 24. Okay. So this 1 1, whatever you defined here, moves up to bit number 24 here. Now not only, but we have to clear these bits first, right? So for clearing the bits, what you need to do is you need to ampersand the complement of this value. So ampersand the one's complement of the value that you obtained here. So if the value was FF, okay, and then for a 32-bit register, this value is going to be FF, and then what all of the rest are going to be zeros. So FF 0 0 0 0. This is what the value is going to be. Okay. When we set this here without the complement, so say so far we have not put in the complement. Okay, we are just, so let's make it clear. So we have not put in the complement, we have not put in the bracket. At this stage, this is the value. Okay. Now what we do is we do the ampersand, we do the complement of this value. So we are doing the complement. So when you do the complement of this value becomes 0 0. Okay, because all ones become zeros and the rest of them become Fs. So this is what you get when you complement it, 0 0 FFF FFF in hex. Now when you AND this value with this register, what happens? So when you are ANDing this value, anything ANDed with a 1 retains that value. So if it was a 0, 0 with 1, 0 and 1 remains a 0. If it was a 1, it remains a 1, and so on. So these values are unaffected. And these values, since if you AND anything with a 0, becomes a 0. So all these values become 0. So only these fields are cleared. So that is the meaning of this expression. You could also have done it this way. You could have left this out here, that is the complement, and you could have ANDed it with the complement here also. So that is also fine. Okay, so both the ways have the same effect. After the complement is done, say we have to configure these ports. Okay, so say configuring these ports as output ports, and then for that, to configure, we'll come to this later, but to configure these fields as output, we have to set them to be 0 1 in each field. Okay, so this means it is set as an output port. So what we do is, again, we declare this as a binary 0 1 0, because expressing this in hex might be a little bit, we'll have to do some calculations in our head. Better to keep it like this so that it's more expressive. We have this value, and then we again left shift it to 24 bits. So now this field is, we have zeroed out this field. So we left shift this new number to 24 bits, and then whatever the register value was, like the previous slide, we OR it. When we OR the value, because since these are all zeros, when we OR the value, this value comes in and sits here. Okay, so this is a way of clearing these values and setting the values. So rotation operator, there is left shift is very important, not rotation. Left shift is very important. And generally, when we need to clear a bit or a sequence of bits, we do a logical and with the complement, then and the ones complement of the bit position. Then, if needed, we can set any bit pattern, like using a logical OR in the same way as scenario 1 after clearing the required bit fields. So that is what we did here. Let's move on. So now another important operation is checking whether a bit is, say, set in a particular a bit is set or cleared in a particular bit position in a register, because that is also something. So we say we have configured some peripheral and we are waiting for the peripheral to be ready, and there is a particular bit associated with that peripheral which would become 1. In this case, it's a PLL. PLL is not a peripheral, but anyway, for the phase lock loop, this is the bit. So this is for anything. So when the bit gets set here to 1, we are going to move on and continue with our program. So until this bit is set, we cannot proceed. Okay. So what we do is we again create a bit and move it to 25 places, because this is bit 25. So move it to 25 places. So this is preparing the bit here. And then what we do is, while not RCCCR ampersand PLL ready. So what we are doing here is, when we do this, if this was a 1, it becomes a non-zero value. So this becomes a non-zero value. So while not non-zero, so this means while not non-zero means while 0. So as long as this value is 0, you are stuck in the loop. The moment the value changes to 1, this condition is falsified. It comes out and continues. So this is something you will see in your programs also quite a bit. So that is one thing. Then coming to pointer arithmetic again. So this is something that you have done in your C standard C code also, but it's worth a mention. That is, whatever, and yesterday we said that whenever a pointer variable is declared, that variable is treated differently. So say a variable is declared as a pointer. So it is like, so when you declare a variable as, say, an int pointer, that is a word wide variable, then when you increment the variable, when you say variable plus plus, okay, if it's a pointer variable and if it's pointing to a word, it is going to advance by 4 bytes. That is, the content of this variable is going to advance by 4 bytes. Okay, that is something you have to keep in mind. 4 bytes would mean not 32 positions, but 4 positions. So we'll see that. We will see that. So say the address of the variable is E000, E000, and then you declare this as an unsigned int 32 pointer, and then you do variable plus plus. This becomes E000, E004. If you have declared it as an unsigned int 32, if you had declared it as an unsigned int 16, then this will be E000, E002. If you make it 8, then it is going to be E000, E001. So this is how the pointers advance based on the type of that pointer.